Hi, in this video I'm going to explain the week 2 lab exercises and do a code walkthrough for them. So the first step is to download the lab exercise PDF. This is where I got some inspiration from. This is a UAV flying over the top of a cow herd, and they're using it to count the cows and check the conditions. So we first of all got to download the modified toolbox. So we'll get that. And then this is the solution. So unzip this like usual. Set up that toolbox. And then I'll go back to the downloads directory and open the solution. So just to make sure that the updated toolbox is working properly, I'm just going to start with lab exercise 2, just make sure that I can actually plot the cows. Okay, so that's okay. If you can plot any more than one cow, then the modified toolbox is working. Okay, so let's move on to the week 2 lab solution, and we'll go through each of the exercises in turn. So remembering that the first exercise, it specifies that you should use Tranimate, which is transform animate, and then you start at the origin. So it's also good to always assume, unless otherwise stated, that the normal coordinate frame, as in x that way, y that way, z up that way, stands and it moves 10 meters off the ground. That's a positive z. So we've got Tranimate from the identity matrix, which is where we're saying it's starting, to a translation of 10, and we've got it moving it as in animating at 25 frames a second. So I'll press F5. It's going to pause at this input command. Press enter there, and then our first animation is that it's moving that transform from the origin up to 10 meters. Then, although you could encode in each of the Tranimates the start and the end, I just, for maybe ease of reading, have this start and end variable which I set to be whatever the start to be the previous end, and then the end to be the new place that we want to move to. So the new place we want to move to is to roll around the x-axis by -10 degrees, and you will notice that that will mean that the y-axis is now pointing down towards the ground. So there's a slight mistake there. It should have been 10 degrees there, and it should be 20 degrees for the second one. Apologies for that. We'll save that and go back to this point again. So the rotation is 10 degrees around this x-axis in the negative direction, so that the y-axis is now pointing more down towards the ground. So now we're going to move translation across. So we're keeping the rotation about the x-axis, and we're translating it. And now we're going to rotate back. So we're going to be rotating around the x-axis again by 10 degrees, but I'm just setting what the end transform I want to see, which is just the translation of z up and y across. So now in this case we're going to rotate around the y-axis by 20 degrees, positive 20 degrees. You can see in this case the x-axis is pointing downwards. Then we're going to translate along the x-axis, so now we're at a position of 2 across in the X, 2 in the Y, and 10 up in the Z. Now we're going to translate. We're going to rotate back again so that we just have that translation and no rotation component. And now we're translating it back down to the ground. So it's a 0 Z value, but we're now at 2, 2 in terms of the X and the Y. You can see that from the top down. 2, 2. Okay, so now for exercise 2, we're going to create the robot cows. The default is to have 2 of those. I haven't deleted the transform from before, just leave it there. Just check that the count is 2, so yes it is. And then we'll plot one single random step. So you can see both of the cows move forward and did some slight rotation. So this instruction is if you wanted to specifically change the original toolbox, but it's probably easier just to download the modified one. So we've created the robot cows, we've checked the cow count, and we've plotted the single random step. So we could also create more cows by passing in the variable here. So as I showed with the robot cow class in the constructor, it takes the parameter cow count. Although it has a default value of 2, you could pass in a different value there if you wanted to change that number. So in this case, we're going to create 10. So we'll clear that figure, delete the original class of cow herd. We enclose it in this try catch just in case it didn't exist. This time we've created 10, so each time it's loading apply model for each of those cows and randomly spawning them in different locations. And we're setting this number of steps, this delay, and then we're going to test the plot many steps to move it through 100 times, pausing by 10 milliseconds each time. So you can see the behavior is as soon as they hit the edge, they turn around and come back again. So now we can query the individual cows. So we've got the cow herd and the cows, and we just want to look at the base of the second cow. So this is the transform of the base of the second cow. So we could find it. We could say x minus 3.7 and y 4.9. So I'd say it's probably this one up here, would be my guess. And we could check that by changing the base, make it back to the start again, and then just plot one random step from there. So you notice how that one's just jumped to the identity matrix, and then it's done one step. Okay, so now for this third exercise, we want to create a cow herd with more than 2 cows, and then we want to plot the UAV moving over the top of it, which was the same as in exercise 1. So first of all, I want to comment out previous exercises so that I can run this one specifically. So I press F5 to run to there. I'll create 3 robot cows, and I'll dock that figure, and then we've got the UAV starting at the identity matrix, so plot that, and then we're going through each of the cows, and we're displaying the location of that cow. Relative to the UAV. And then we're just moving the cows one step again. So let's determine the transform between the UAVs and each of the cows. So notice this is done by doing the inverse UAV transform multiplied by the specific cow base. Then we're going to go through each of the steps in exercise 1. So here I've just put these as being the UAV transforms. So this is the specific transforms that I want it to move through. Storing all these in a cell array. So I've got 9 cells there. And then we're going to step through each of these steps of the trajectory and use Tranimate to animate the transform at each one of those, between each one of those, and update the cow herd with this plot single random step. Once again, getting the transforms between the UAVs and the cows, each of the cows. So now if I put a breakpoint there and let it run all the way through, then you can see that each one of these steps we're letting the cows move one step, and then we're animating the transform of the UAV. In this last exercise 3.6 of 3, which is to create a cow herd with just one cow, and then to have your single drone moving over the top of the cow. So in order to work out where the drone needs to be, you need to first check where the cow is, and then move your drone accordingly, or move your UAV accordingly so that it stays 5 meters above. So we will clear the figure, create a single cow. We'll start the UAV at the origin, and then we'll translate it up 5 meters. So it moves up. And then I've stepped through 100 times here. It doesn't, it's arbitrary as in how many steps you take, but each time I first work out what the transform of the UAV currently is, and then what the goal of the UAV is, and the goal of the UAV is based upon the cow's base, translated up by 5 meters in the Z direction, and then I transform the UAV accordingly. So I can now let that run. You can see that it's following the cow around. Okay, I'll stop it there. So exercise 4 is this simple 3-link manipulator, and we've got a diagram of it here. So each of the link lengths are 1 meter, and of course they're revolute joints rotating about the Z-axis always. And then you need to fill in these parameters. So this is a much simpler example than the example of the Puma 560 robot, which was given in another video. So the only thing we really need to worry about is the translation along the x-axis. There's no translation along the z-axis. There's no rotation. And then we also need to know what the joint angle is. So in week 3 material, there's this DH reference guide, which might be useful. All this material is in the textbook, but this is a brief summary of it that might be useful for the week 3 lab exercises. So we can see that there's a rotation about the z-axis by the angle theta, which is the joint angle. And there's a translation along the z-axis by d, and then there's a translation along the x-axis by a, and a rotation about the x-axis by alpha. So in our case here, we just have the translation along the x-axis. So it's only the a that has any value put in it. D would be 0, a would be 1 meter, alpha would be 0, offset you could put in, but it's irrelevant. Then you create the robot with the serial link command, set it all to 0. This workspace, you can choose whatever workspace you want, but for this case, because we know that the maximum that it can be fully extended is 2 meters, then maybe 4 plus or minus 4 is probably a reasonable number to choose for that, and then to plot it. So the purpose of this exercise was to get you to think about a very simple DH example and then to use the teach command to move it around, have a look what the joint angles do and which values in X, Y, Z roll pitch yaw it's able to change. So I'll show you this example. I first comment out the previous ones. Don't run those. So as you can see, D0, alpha 0, no offset, it defaults to 0. The Q limits are chosen to be plus or minus 180, although perhaps you could think about possible self-collisions that could happen because of those joint limits. But the only parameter we actually need to have a value for is A. So we've created the robot, got the workspace being plus or minus 4 meters, setting the joint values to be 0 radians, and then now we're plotting it. So it's interesting to use this teach interface to see what the XYZ roll pitch yaw is and see how changes in the joint angles affect each of these parameters. So you can notice straight away that these two, Z, is not changing at all. No matter what joint angle we choose for joints 1, 2, and 3, we can't actually affect the Z position. And the other thing we can't affect is the roll and the pitch. So that's the rotation around the x-axis and the rotation about the y-axis. We can change the rotation about the z-axis. We can use this get pos to tell us what the current angle is set at. This is in radians. Another useful function, other than timesing it by 180 on pi to change to degrees, which you could do, is you can use rad2deg. That does the same thing. And then we can just check on the Q limits. So we had set them here with plus or minus pi. You can see that this is the value here as well. You can do rad 2 degrees again. You see that they're plus or minus 180. But you might be able to notice that if I move joint 2 all the way to its maximum limit, it actually starts to self-collide, and in the same way joint 3 as well. If I move it, it can self-collide with it itself. Okay, so I hope that was useful for you, and if you've got any comments or suggestions, then add it to the discussion board. If you think I missed anything or got something wrong, then add it to the discussion board. Otherwise I'll see you on Wednesday.